Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from ServiceNow, GroundCoa, and GroundNext, high-quality desktop grounding for computer use agents. Modern AI agents are getting good at planning what to do on a computer, but they still struggle with a crucial step, actually clicking the right thing on the screen. To be truly useful, a computer use agent has to translate a natural language instruction like open the color picker into a precise action on a specific icon or menu item. That's the grounding problem. On desktop applications, this is especially hard. Screens are high resolution, packed with tiny, similar-looking elements, and full of user-specific content. A single misclick can derail the entire task. This work tackles desktop grounding head-on with two main contributions. First, the authors introduce GroundCoa, a large, carefully annotated dataset of real desktop interactions. Second, they build GroundNext, a family of vision language models trained on this data to map instructions to the correct UI elements. Despite being relatively small, 3 billion and 7 billion parameters, these models reach state-of-the-art performance on multiple benchmarks, using less than a tenth of the training data of many prior systems. The central message is that high-quality, expert-driven data can beat brute force scale. GroundCoa is built from expert annotators actually using desktop applications. Their sessions are captured as screenshots, and then nearly every visible UI element is labeled with a bounding box and metadata. In total, the dataset includes about 56,000 screenshots and more than 3.5 million human-verified annotations. These come from 87 different applications spanning 12 categories, such as office tools, CAD, development environments, creative apps, and more. The result is a dense, realistic snapshot of how real desktops look during real tasks. Desktop screenshots in GroundCoa range from about 0.5 megapixel up to 7 megapixels. Within those images, many UI elements are very small, icons, sliders, and subtle controls that occupy only a tiny fraction of the screen. On top of that, many tools look similar, multiple icons with related shapes, or menus with nearly identical labels. The dataset also captures user-specific content, like open documents or spreadsheets, which the model has never seen before. All of this makes precise localization and disambiguation a genuine challenge, and it's exactly the kind of difficulty a real computer use agent must handle. GroundCoa doesn't just mark boxes on the screen. It also encodes what those boxes represent. Many elements are tagged with semantic types like button, menu, slider, or information display. And about half of all elements have this fine-grained categorization. The dataset also includes multiple variants of similar applications, such as different office suites. That forces models to learn subtle, application-specific grounding strategies instead of memorizing a single layout. This richer structure is crucial for building agents that can generalize across the messy diversity of real desktop software. To turn raw annotations into training data for grounding, the authors start from expert demonstrations. Each demonstration yields screenshots plus detailed UI metadata. From this, they generate natural language instructions that reflect what a user might actually want to do, like changing a color, opening a menu, or selecting a specific tool. This process produces around 700,000 image instruction pairs for supervised fine-tuning. The instructions are grounded in real workflows, so the model learns to connect everyday language to concrete UI actions. On top of GroundCoa, the authors build GroundNext, a family of compact vision language models. There are two main sizes, 3 billion and 7 billion parameters. These models are tailored for the grounding task. Given a screenshot and an instruction, they predict the target UI element. Training happens in two stages. First, supervised fine-tuning on the 700,000 curated examples teaches the basic mapping from language to screen regions. Then, reinforcement learning further sharpens the model's decisions. The result is a set of models that are both accurate and efficient enough to be practical in larger agent systems. The first training stage is supervised fine-tuning. Here, GroundNext sees hundreds of thousands of examples where the correct target element is known. It learns to map from the screenshot and instruction to the right bounding box. The authors evaluate these SFT-only models on 5 demanding benchmarks that test grounding across different domains and interfaces, at both 3 and 7 billion parameters. GroundNext, with just supervised training, already delivers the best average performance among the compared models, despite using far less training data than many competitors. This underscores the impact of carefully curated, high-quality supervision. After supervised fine-tuning, the authors apply reinforcement learning on a smaller set of about 10,000 ground QA examples. The idea is straightforward. The model proposes a target element, and it receives a reward based on whether that choice is correct. Even with this relatively simple, verifiable reward signal, RL consistently improves performance across benchmarks. The gains are visible on top of already strong SFT baselines, showing that reinforcement learning can fine-tune the model's decision boundaries and make its grounding more precise. This slide highlights the quantitative impact of reinforcement learning on GroundNext. You can see how both the 3 billion and 7 billion parameter models improve over their supervised-only versions, and how they compare to other strong baselines across multiple grounding benchmarks. The key pattern is that RL consistently pushes GroundNext to the top of the leaderboard, confirming that even a modest amount of reward-based training can significantly sharpen grounding performance when built on top of high-quality supervised data. Grounding isn't just an isolated benchmark task, it's a core component of full computer use agents. To test this, the authors plug GroundNext into an agent pipeline on the OS World verified benchmark, using a powerful model O3 as the planner. In this setup, GroundNext is responsible for turning planned actions into concrete clicks and selections. Remarkably, the 3 billion parameter GroundNext model performs on par with, or better than, much larger and even proprietary systems. This demonstrates that strong grounding can directly translate into better end-to-end task completion on real desktop workflows. To probe generalization, the authors evaluate GroundNext across a wide range of domains: CAD tools, development environments, creative software, scientific apps, office suites, and operating system interfaces. Additional benchmarks test cross-platform behavior on Windows, macOS, Linux, mobile, and web-like UIs. Overall, GroundNext is robust, maintaining strong performance across these varied settings. At the same time, error analyses reveal that rare UI patterns, ambiguous icons, or unusual layouts can still trip the model up, pointing to directions for future data collection and model design. Even with strong overall performance, GroundNext is not perfect. Visualizations of its mistakes show common failure modes: picking the wrong icon when several look alike, clicking a nearby element instead of the intended one, or missing very small targets. Sometimes the model misinterprets the instruction relative to the current UI state. For example, when a required panel is hidden. These errors suggest that future work could benefit from more expressive reward functions, better modeling of UI context and state, and perhaps multi-step reasoning about what needs to be visible before an action can succeed. Stepping back, this work makes a clear case for investing in data quality for grounding. GroundQA provides dense, expert-annotated coverage of real desktop interfaces, capturing the complexity and diversity that agents will face in practice. On top of this, the GroundNext models show that relatively small vision language systems can achieve state-of-the-art grounding performance when trained on the right data, and that reinforcement learning with simple, verifiable rewards can further refine their behavior. Together, these pieces form a strong foundation for building reliable, general-purpose computer use agents that can handle complex tasks across many desktop applications. The authors close by outlining several future directions. First, GroundQA can support larger models and more extensive fine-tuning, potentially pushing performance even higher. Second, its dense annotations open the door to more sophisticated reward designs for reinforcement learning, beyond the simple correctness signal used here. Third, combining desktop data with web and mobile grounding datasets could yield agents that move seamlessly across platforms, though balancing these domains will be non-trivial. Finally, the dataset's rich metadata, like platform and application categories, can fuel research on continual learning, where agents adapt to new software and interaction patterns over time instead of remaining static.